The Graphics Interchange Format is a bitmap image format that was developed by US-based software writer Steve Wilhite while working at the Internet service provider CompuServe in 1987 and has since come into widespread usage on the World Wide Web due to its wide support and portability. The format supports up to 8 bits per pixel for each image, allowing a single image to reference its own palette of up to 256 different colors chosen from the 24-bit RGB color space. It also supports animations and allows a separate palette of up to 256 colors for each frame. These palette limitations make the GIF format less suitable for reproducing color photographs and other images with continuous color, but it is well suited for simpler images such as graphics or logos with solid areas of color. GIF images are compressed using the Lempels-Welch lossless data compression technique to reduce the file size without degrading the visual quality. This compression technique was patented in 1985. Controversy over the licensing agreement between the software patent holder, Unisys, and CompuServe in 1994 spurred the development of the portable network graphics standard. By 2004 all the relevant patents had expired. History: CompuServe introduced the GIF format in 1987 to provide a color image format for the file downloading areas, replacing their earlier run-length encoding format, which was black and white only. GIF became popular because it used LZW data compression, which was more efficient than the run-length encoding that formats such as PCX and Mac Paint used, and fairly large images could therefore be downloaded in a reasonably short time, even with very slow modems. The original version of the GIF format was called 87A. In 1989, CompuServe released an enhanced version called 89A, which added support for animation delays, transparent background colors, and storage of application-specific metadata. The 89A specification also supports incorporating text labels as text, but as there is little control over display fonts, this feature is not widely used. The two versions can be distinguished by looking at the first 6 bytes of the file, which, when interpreted as ASCII, read GIF 87A and GIF 89A, respectively. GIF was one of the first two image formats commonly used on websites, the other being the black and white XBM. In September 1995, Netscape Navigator 2.0 added animated GIF support. The feature of storing multiple images in one file, accompanied by control data, is used extensively on the web to produce simple animations. The optional interlacing feature, which stores image scan lines out of order in such a fashion that even a partially downloaded image was somewhat recognizable, also helped GIF's popularity, as a user could abort the download if it was not what was required. As a noun, the word GIF is found in the newer editions of many dictionaries. In 2012, the American wing of the Oxford University Press recognized GIF as a verb as well, meaning to create a GIF file, as in GIFing was perfect medium for sharing scenes from the Summer Olympics. The press's lexicographers voted it the word of the year, saying that GIFs have evolved into a tool with serious applications including research and journalism. In May 2015, Facebook added GIF support after originally rejecting support. Pronunciation: the creators of the format pronounced GIF as GIF with a soft G, DF as in gin. Steve Wilhite says that the intended pronunciation deliberately echoes the American peanut butter brand GIF, and CompuServe employees would often say, "Choose your developers choose GIF," spoofing this brand's television commercials. An alternative pronunciation with a hard G is in widespread usage. The American Heritage Dictionary cites both, acknowledging GIF as the primary pronunciation, while while Cambridge Dictionary of American English offers only the hard G pronunciation. Merriam-Webster's Collegiate Dictionary and the OED cite both pronunciations, but place GIF in the default position. The New Oxford American Dictionary gave only GIF in its second edition, but updated it to GIF in its third edition. The disagreement over the pronunciation led to heated internet debate. On the occasion of receiving a Lifetime Achievement Award at the 2013 Webby Award ceremony, Wilhite rejected the alternative pronunciation, and his speech led to 17,000 posts on Twitter and 50 news articles. The White House and TV program Jeopardy! Also waded into the debate during 2013. Usage GIFs are suitable for sharp-edged line art with a limited number of colors. This takes advantage of the format's lossless compression, which favors flat areas of uniform color with well-defined edges. GIFs may be used to store low-color sprite data for games. GIFs can be used for small animations and low-resolution film clips. GIFs are commonly used as a medium for humorous effect. One or more video sources can be edited, rearranged, or combined to create an absurd juxtaposition, to create the opposite effect intended by the creator of the original work, or to emphasize and exaggerate a minor detail. File format. Conceptually, a GIF file describes a fixed-sized graphical area populated with 0 or more images. Many GIF files have a single image that fills the entire logical screen. Others divide the logical screen into separate sub-images. The images may also function as animation frames in an animated GIF file, but again these need not fill the entire logical screen. GIF files start with a fixed-length header giving the version, followed by a fixed-length logical screen descriptor giving the size and other characteristics of the logical screen. The screen descriptor may also specify the presence and size of a global color table, which follows next if present. Thereafter, the file is divided into segments, each introduced by a 1-byte sentinel, an image, an extension block, the trailer, which should be the last byte of the file, An image starts with a fixed-length image descriptor, which may specify the presence and size of a local color table. The image data follows, 1 byte giving the bit width of the unencoded symbols, followed by a linked list of subblocks containing the LZW encoded data. Extension blocks consist of the sentinel, an additional byte specifying the type of extension, and a linked list of subblocks with the extension data. Extension blocks that modify an image must immediately precede the segment with the image they refer to. The linked lists used by the image data and the extension blocks consist of series of subblocks, each subblock beginning with a byte giving the number of subsequent data bytes in the subblock. The series of subblocks is terminated by an empty subblock. This structure allows the file to be parsed even if not all parts are understood. A GIF marked 87 may contain extension blocks. The intent is that a decoder can read and display the file without the features covered in extensions. It does not understand. The full detail of the file format is covered in the GIF specification. Palettes. GIF is palette-based. The colors used in an image in the file have their RGB values defined in a palette table that can hold up to 256 entries, and the data for the image refer to the colors by their indices in the palette table. The color definitions in the palette can be drawn from a color space of millions of shades, but the maximum number of colors a frame can use is 256. This limitation seemed reasonable when GIF was developed because few people could afford the hardware to display more colors simultaneously. Simple graphics, line drawings, cartoons, and grayscale photographs typically need fewer than 256 colors. Each frame can designate one index as a transparent background color. Any pixel assigned this index takes on the color of the pixel in the same position from the background, which may have been determined by a previous frame of animation. Many techniques, collectively called dithering, have been developed to approximate a wider range of colors with a small color palette by using pixels of two or more colors to approximate in-between colors. These techniques sacrifice spatial resolution to approximate deeper color resolution. While not part of the GIF specification, dithering can of course be used in images subsequently encoded as GIF images. This is often not an ideal solution for GIF images, both because the loss of spatial resolution typically makes an image look fuzzy on the screen, and because the dithering patterns often interfere with the compressibility of the image data, working against GIF's main purpose. In the early days of graphical web browsers, graphics cards with 8-bit buffers were common, and it was fairly common to make GIF images using the WebSafe palette. This ensured predictable display, but severely limited the choice of colors. Now that 32-bit graphics cards, which support 24-bit color, are the norm, palettes can be populated with the optimum colors for individual images. A small color table may suffice for small images, and keeping the color table small allows the file to be downloaded faster. Both the 87A and 89A specifications allow color tables of 2n colors for any n from 1 through 8. Most graphics applications will read and display GIF images with any of these table sizes, but some do not support all sizes when creating images. Tables of 2, 16, and 256 colors are widely supported. True color. Although the GIF format is almost never used for true color images, it is possible to do so. A GIF image can include multiple image blocks, each of which can have its own 256 color palette, and the blocks can be tiled to create a complete image. Alternatively, the GIF 89A specification introduced the idea of a transparent color where each image block can include its own palette of 255 visible colors plus one transparent color. A complete image can be created by layering image blocks with the visible portion of each layer showing through the transparent portions of the layers above. To render a full-color image as a GIF, the original image must be broken down into smaller regions having no more than 255 or 256 different colors. Each of these regions is then stored as a separate image block with its own local palette, and when the image blocks are displayed together, the complete full-color image appears. For example, breaking an image into tiles of 16 by 16 pixels ensures that no tile has more than the local palette limit of 256 colors, although larger tiles may be used and similar colors merged, resulting in some loss of color information. Since each image block requires its own local color table, a GIF file having lots of image blocks can be very large, limiting the usefulness of full-color GIFs. Additionally, not all GIF rendering programs handle tiled or layered images correctly. Many rendering programs interpret tiles or layers as animation frames and display them in sequence as an endless animation, with most web browsers automatically displaying the frames with a delay time of 0.1 seconds or more. Example GIF file. Microsoft's Paint program saves a small black and white image as the following GIF file. Paint does not make optimal use of the GIF format due to the unnecessarily large color table and symbol width. This GIF file is not an efficient representation of the 15-pixel image. Although the graphics control extension block declares color index 16 to be transparent, that index is is not used in the image. The only color indexes appearing in the image data are decimal 40 and 255, which the global color table maps to black and white, respectively. Note that the hex numbers in the following tables are in little-endian byte order, as the format specification prescribes. Byte hexadecimal text or value meaning 0474946383961 GIF 89A header logical screen descriptor 60300 logical screen width in pixels 80500 logical screen height in pixels AF7 GCT follows for 256 colors with resolution 3 by 8 bits. Primary, the lowest 3 bits represent the bit depth -1. The highest true bit means that the GCT is present. COO default pixel aspect ratio RGB global color table D 0000000 color number 0 black 10 to 80 0000128 color number 1 to 85 0000000 color number 40 black 30 AFFFFF 255,255,255 color number 255 white 30D 21 F9 graphic control extension 30 F04 4 bytes of GCE data follow 310.01. There is a transparent background color 311.000 delay for animation in hundredths of a second. Not used 313 to 1016 color number 16 is transparent 314.00 end of GCE block 315 to 2C image descriptor 316.0000 NW corner position of image in logical screen 31A 03.0005.00 image width and height in pixels 31E 00 no local color table 31F088 start of image LZW minimum code size 320 to 0B11 to 11 bytes of LZW encoded image data follow 32C00 end of image data 32D 3B GIF file terminator image coding the image pixel data scanned horizontally from top left are converted by LZW encoding to codes that are then mapped into bytes for storing in the file. The pixel codes typically don't match the 8-bit size of the bytes, so the codes are packed in 2 bytes by a little-endian scheme. The least significant bit of the first code is stored in the least significant bit of the first byte. Higher-order bits of the code into higher-order bits of the byte, spilling over into the low-order bits of the next byte as necessary. Each subsequent code is stored starting at the least significant bit not already used. This byte stream is stored in the file as a series of subblocks. Each subblock has a maximum length 255 bytes and is prefixed with a byte indicating the number of data bytes in the subblock. The series of subblocks is terminated by an empty subblock. For the sample image above, the reversible mapping between 9-bit codes and bytes is shown below. A slight compression is evident. Pixel colors defined initially by 15 bytes are exactly represented by 12 code bytes including control codes. The encoding process that produces the 9-bit codes is shown below. A local string accumulates pixel color numbers from the palette with no output action as long as the local string can be found in a code table. There is special treatment of the first 2 pixels that arrive before the table grows from its initial size by additions of strings. After each output code, the local string is initialized to the latest pixel color. Table 9-bit string and GT code action number 000H initialize root table of 9-bit codes palette colors number 255 0FFHCLR 100H and 101 1H 100H clear pixel local color palette string black number 402802H first pixel always to output white number 255FF string found in table 28FF 102H always add first string to table FF initialize local string white number 255FFFF string not found in table 0FFH output code for previous string FFFF 103H add latest string to table FF initialize local string white number 255FFFF string found in table black number 40FFFF28 string not found in table 103H output code for previous string FFFF28 104H add latest string to table 28 initialize local string white number 25528FF string found in table white number 25528FFFF string not found in table 102H output code for previous string 28FFFF 105H add latest string to table FF initialize local string white number 255FFFF string found in table white number 255FFFF string not found in table 103H output code for previous string FFFFF 106H add latest string to table FF initialize local string white number 255FFFF string found in table white number 255FFFF string found in table white number 255FFFFF string not found in table 106H output code for previous string FFFFFF 107H add latest string to table FF initialize local string white number 255FFFF string found in table white number 255FFFF string found in table white number 255FFFFF string found in table no more pixels 107H output code for last string 101H end for clarity the table is shown above as being built of strings of increasing length. The scheme can function, but the table consumes an unpredictable amount of memory. Memory can be saved in practice by noting that each new string to be stored consists of a previously stored string augmented by one character. It is economical to store at each address only 2 words, an existing address and 1 character. The LZW algorithm requires a search of the table for each pixel. A linear search through up to 4096 addresses would make the coding slow. In practice, the codes can be stored in order of numerical value. This allows each search to be done by a SAR with only 12 magnitude comparisons. For this efficiency, an extra table is needed to convert between codes and actual memory addresses. The extra table upkeeping is needed only when a new code is stored, which happens at much less than pixel rate. Image decoding. Decoding begins by mapping the stored bytes back to 9-bit codes. These are decoded to recover the pixel colors as shown below. A table identical to the one used in the encoder is built by adding strings by this rule as incoming code found in table. Yes, add string for local code followed by first byte of string for incoming code. No, add string for local code followed by copy of its own first byte. Shift 9-bit and GT local table pixel code and GT string palette color action 100H 0OH number 0 initialize root table of 9-bit codes. Palette colors 0FFH number 255 100H CLR 101H N028H number 40 black decode first pixel 0FFH028H incoming code found in table number 255 white output string from table 102H 28FF add to table 103H 0FFH incoming code not found in table 103H FFFF add to table output string from table number 255 white number 255 white 102H 103H incoming code found in table output string from table number 40 black number 255 white 104H FFFF28 add to table 103H 102H incoming code found in table output string from table number 255 white number 255 white 105H 28 FFFF add to table 106H 103H incoming code not found in table 106H FFFFF add to table output string from table number 255 white number 255 white number 255 white 107H 106H incoming code not found in table 107H FFFFFF add to table output string from table number 255 white number 255 white number 255 white number 255 white 101H and LZW code lengths. Shorter code lengths can be used for palettes smaller than the 256 colors in the example. If the palette is only 64 colors, the symbols can range from 0 to 63, and the symbol width can be taken to be 6 bits, with code starting at 7 bits. In fact, the symbol width need not match the palette size, as long as the values decoded are always less than the number of colors in the palette. The symbols can be any width from 2 to 8, and the palette size any power of 2 from 2 to 256. For example, if only the first 4 colors of the palette are used, the symbols can be taken to be 2 bits wide with code starting at 3 bits. Conversely, the symbol width could be set at 8, even if only values 0 and 1 are used. These data would only require a 2-color table, although there would be no point in encoding the file that way. Something similar typically happens for bicolor images. The minimum symbol width is 2, even if only values 0 and 1 are used. The code table initially contains codes that are 1 bit longer than the symbol size in order to accommodate the 2 special codes CLR and END, and codes for strings that are added during the process. When the table is full, the code length increases to give space for more strings, up to a maximum code 4095 equals FFF. As the decoder builds its table, it tracks these increases in code length, and it is able to unpack incoming bytes accordingly. Uncompressed GIF. The GIF encoding process can be modified to create a file without LZW compression that is still viewable as a GIF image. This technique was introduced originally as a way to avoid patent infringement. Uncompressed GIF can also be a useful intermediate format for a graphics programmer because individual pixels are accessible for reading or painting. An uncompressed GIF file can be converted to an ordinary GIF file simply by passing it through an image editor. The modified encoding method ignores building the LZW table and omits only the root palette codes and the codes for clear and stop. This yields a simple encoding but sacrifices all of the compression. Each pixel in the image generates an output code indicating its color index. When processing an uncompressed GIF, a standard GIF decoder will not be prevented from writing strings to its dictionary table, but the code width must never increase since that triggers a different packing of bits to bytes. If the symbol width is n, the codes of width n plus 1 fall naturally into two blocks. The lower block of 2 encodes for coding single symbols, and the upper block of 2 encodes that will be used by the decoder for sequences of length greater than 1. Of that upper block, the first two codes are already taken, 2n for clear and 2n plus 1 for stop. The decoder must also be prevented from using the last code in the upper block 2n plus 1 minus 1, because when the decoder fills that slot, it will increase the code width. Thus in the upper block there are 2n minus 3 codes available to the decoder that won't trigger an increase in code width, because the decoder is always one step behind in maintaining the table. It does not generate a table entry upon receiving the first code from the encoder, but will generate one for each succeeding code. Thus the encoder can generate 2n-2 codes without triggering an increase in code width. Therefore the encoder must emit extra clear codes at intervals of 2n-2 codes or less to make the decoder reset the coding dictionary. The GIF standard allows such extra clear codes to be inserted in the image data at any time. The composite data stream is partitioned into sub-blocks that each carry from 1 to 255 bytes. For the sample 3x5 image above, the following 9-bit codes represent clear followed by image pixels in scan order and stop. 9-bit codes 100,028 101. After the above codes are mapped to bytes, the uncompressed file differs from the compressed file, thus 320 to 1420 20 bytes uncompressed image data follow 33500 and compression example. The trivial example of a large image of solid color demonstrates the variable length LZW compression used in GIF files. The code values shown are packed into bytes, which are then packed into blocks of up to 255 bytes. A block of image data begins with a byte that declares the number of bytes to follow. The last block of data for an image is marked by a 0 block length byte. Interlacing. The GIF specification allows each image within the logical screen of a GIF file to specify that it is interlaced, i.e., that the order of the raster lines in its data block is not sequential. This allows a partial display of the image that can be recognized before the full image is painted. An interlaced image is divided from top to bottom into strips 8 pixels high, and the rows of the image are presented in the following order: pass 1, line 0 from each strip; pass 2, line 4 from each strip; pass 3, lines 2 and 6 from each strip; pass 4, lines 1, 3, 5, and 7 from each strip. The pixels within each line are not interlaced, but presented consecutively from left to right. As with non-interlaced images, there is no break between the data for one line and the data for the next. The indicator that an image is interlaced is a bit set in the image's header block.